much faster than
Today we're going to discuss how to teach logical thinking through logic programming with a focus on non-computing students and starting already at the earliest level, namely in primary school. I have a number of questions that I've suggested that we consider, but it's not essential. I think anyone who has experience and has been thinking about this will have their own thoughts in any case. But there are some issues that have come up in the past, issues concerning the extent to which it's feasible or desirable to start at least teaching logic programming or logical thinking rather from a purely declarative approach. And if that's the case, whether or not problem solving and reasoning would also be part of the course at some stage, whether or not the usual syntax of symbolic logic, Prolog, ASP, and other logic programming languages would be used at the earliest stages, or would natural language readings or even natural language syntax be adequate for many purposes? And in particular, do people feel that it's necessary to teach formal semantics? And if so, would that be an obstacle to the teaching? So at the moment, there's we need to teach programming or program specification, but that it might be adequate to focus on, say, knowledge representation, declarative representations, and natural language readings. If that's not the case, then please say so. And that's the purpose of this meeting. So I have a proposed list of presenters. And the original brief was that everyone would speak for 2 minutes with a discussion of 2 minutes, but I think it's not going to work. So we're going to just try to see how many presentations and discussions we can fit in today, and if necessary, spill over into next week, perhaps, if that's all right, Veronica. And we'll see to what extent we can deal with administrative matters, either through email or some other venue. Okay, so Laura, over to you. I've got your presentation here, so please speak to what you've already been thinking. Thank you.
Okay,
Laura.
thank you. Well, our experience is with children, and Jorge and I have been teaching LP through Prolog to children between 7 and 12 years old. I think the surprising thing is that some of them just are beginning to write at the age of 7. So they're just knowing how to write, and they know just a little mathematics. What do we teach? Well, we address the natural language to LP approach. Of course, we teach knowledge representation because we teach to recognize relations between objects. That is associated with our aim to teach logical thinking. One example, for example, is Laura loves chocolate, and we help them to recognize the object, Laura chocolate, and the relation. We employ the problem-based learning approach through which students develop the problem-solver skills as part of their computational thinking abilities. The problem that we face here is identifying who stole my suitcase. And with this problem, we develop all the experience. We don't think it is necessary to teach formal semantics to children. I think we shouldn't. Just an informal explanation is enough. While children can identify simple rules in natural language, they can read, understand, and write simple rules in Prolog, fostering a connection to logical thinking. I think I must define what we think is logical thinking. And when we begin with this experience, we notice that there is no full consensus between what is logical thinking. So Veronica, Jorge, and I present our own definition, and perhaps I can read it. This definition is in the paper of the 50 years celebration of Prolog. It's in the paper we wrote there. Logical thinking mainly focus on the abilities needed to identify entities, object, and concept. That's why our aim is to teach them how to recognize objects and their relations. To understand, incorporate, and soundly use the rules of logical inference relevant to deriving new implicit ideas in everyday activities. And I think this is a key point to transfer the logical things that we taught at the school to everyday activities. And to reason about these rules and relationship, and judiciously choose among different logical formulation of a same problem. So that is what we mean with logical thinking. And I think one of the most important things is to transfer the teaching that we are doing with children, but that they can transfer it to everyday activities. That is the point. Well, here is an example of rule reading and understanding that we use. And there is a simple rule in Blockly Prolog that we use it instead of textual one. Bueno, finally, we teach deductive reasoning to solve problems, again, associated with logical thinking. We do not teach, and perhaps if Bob can show me the last part. Yes, thank you. We don't teach text-based Prolog, formal syntax, because they are children, so just something like the variables are in capital letters or something like that, but not the other thing. We don't teach formal semantics. We don't teach operational semantics. Nevertheless, we believe that our students may intuitively adopt the backward chaining approach, starting from the query. The query is, who is the thief? Who stole my suitcase? And we think that they adopt the backward chaining approach from this query, following the corresponding rules. And we do not teach, of course, negation as failure. I think I answer all the questions. I don't know if it is something that is missing.
Okay, that's very much. Thank you very much indeed. Let me just ask one question. Do none of your examples involve negation in the rules? So there's no negation in your rules, I guess.
I couldn't understood. Can you please repeat, because it was my internet is not good.
My
I think,
internet
Bob, your
is not
voice is
good.
breaking. Your voice is also breaking.
Yes, my internet is also challenged. So my question is, do your rules contain negation, even though you don't teach negation as failure?
No. We it's just I don't know if it call it purely Prolog, but we have no negation at all.
Good. Any other questions, comments?
So you said you do teach them a little bit about how to reason, or how to draw logical inferences and those type of things, or just interpret it declaratively? I mean, you said something about goal directed, where you have a goal and then they're trying to see if they can solve that goal. I remember seeing that. So you do teach that aspect a little bit.
Sometimes they discover the thief without programming. So if they can discover the thief without programming, they are doing backend chaining from the query, from the rules that they discover. And this is a kind of deductive reasoning. For us, it's not so good because they discovered the thief without programming, and they said, this is the thief. No, we want them to program and make the logic program, but sometimes they can't discover it without, because they make the backward chaining approach.
I see what you mean. Okay.
You understand? Okay.
But then they
do you try to relate it? Do you try to relate their discovery themselves and what the program says? Okay.
And sometimes they find another relationships. For example, if there is sometimes some of our clue included that the thief has a hat, for example, and I have a hat. When I go there, I have a hat, and they began to say, "Well, you are the thief." So, I know someone who have glasses, or someone who have, and they made a lot of relationship with their normal activities. They can play, they are in the game, but they are outside too. They can mix both things. They play the game and the activities, the normal activities that they have outside the school.
May I suggest that this is an experiment on our part? We're not very sure how it's going to go. So let me thank you, Laura, and suggest that we move on to our next presentation. And of course, at some point we may have a more general discussion.
If I may, I want to point out there are very interesting comments in the chat. I will try them to add at the end in a message, but just to let you know.
Okay, thank you. Michael, hello, Michael. This is the first time you've joined us. It's good to see you. Do I see you?
Michael, you're muted. Yeah, just unmute.
Yes, I'm trying.
Okay, we hear you.
I've got a new computer, so I don't know exactly what it's doing. Can you hear me now?
Yes, indeed. Thank you.
Okay. So I'm going to try to answer the questions I've got. First, about my experience. I taught logic programming to high school and sometimes middle school students. I, of course, taught a lot of logic programming to students at university, but I'm not going to talk about it right now. So what tools did we use? We have a system called Spark, which is basically a version of answer set Prolog or just Prolog with sorts. It allows to ask Prolog-like queries. The difference is it answers yes, no, or unknown. So you can talk about information which is not known. It can also compute answer sets, so they're parts relevant to the problem. So the first question, we propose introducing Prolog ASP Datalog declaratively. Can you move down, please? Can you move the slide down? Okay, thank you. I don't teach it purely declaratively. I start with declarative representation, but pretty quickly I move to informal description of simple reasoning algorithms. And it can be top-down, it can be bottom-up, depending on the problem. But still, emphasis is on declarative representation. Teaching problem solving and reasoning. Again, can you move down, please? Yes, but I'm really stressing problem solving. I cannot define logical reasoning right now. I know it when I see it, but my emphasis is on one part of logical reasoning. Let's say taking language seriously, which means before you solve a problem, you have to understand it. And so you have to take rigorous formalization. And I'm trying to almost force them to be as rigorous as they can. And I test what they suggest, or they test what they suggest using this system. They don't know in the beginning how it works, they just use it. Would you focus on the symbolic syntax exclusively? Or would you emphasize? Okay. Okay. I always ask them to formulate rules they're going to write in English, as I said, as rigorously as they can. Only after that, they write it in formal syntax because they need to run it. So there's no emphasis on formal syntax. Do we really need to teach the formal semantics? No, but I believe there's a need to teach difference between formal language and natural language, and between symbols and their models. I believe that's important. But at this level, I don't give any formal definitions of the semantic. And when I give this formal definition, informal definition, I use what I call a rationality principle. So basically say, you are going to build your set of beliefs, all which is given to you, your rules. So your beliefs must satisfy your rules. And the rationality principle, believe nothing you are not forced to believe. As you notice, I'm talking about beliefs here, not about truth, as commonly done in classical logic. But I believe at this level it's not really that important. They will not be able to see the difference clearly, most likely. Okay, anything else there?
Thank you.
Let me just go ahead.
No, this point about truth versus belief, I think is very interesting and be very important, because when you reason hypothetically, you take a hypothetical scenario, it doesn't mean that you're dealing with truth. You're dealing with assumptions that you assume to be true, and those are the kind of tentatively held beliefs, perhaps, or beliefs for the sake of argument.
That's what I strongly believe. And also you have negation as failure. So when you add new information, what you derive is not going to be truth anymore. I prefer to talk about beliefs. For me, truth is what stands, kind of not changed by new information. But it's a almost philosophical, or pseudo-philosophical question, okay?
I think that's fair. I agree that that's very interesting. And I think I like it a lot to start with belief, because truth you can get into arguments, right? Because there are true things, and people can disagree on what's true or don't know, etc. But for example, I don't mean to pick on Laura, but Laura gave a rule that said you speak Spanish if you were born in Argentina. And I would say, no, that's not true, because you could be born in Argentina, but if you moved as an infant to the United States, you'd be speaking English. And so that's going through my head, where if you said, I would say raised in Argentina, but this is not relevant, particularly relevant, other than to say that my mental processes went off in a tangent because I was thinking about truth. But if I thought about belief, I could say, oh yeah, you could believe that. It might not be exactly true, but it's close enough, Anyway, so I think that's a good way to short circuit the literalists like I am from getting sidetracked on irrelevant details.
I also would say, I'm sorry, go ahead.
Oh, sorry, no, go ahead.
Would you mention sometime facts that are true in all the stable models as being particularly interesting when you have multiple stable models?
I missed the beginning of the question. What about truth?
In this framework, when it turns out that something is true in multiple belief systems or multiple stable models, would you kind of point that out as particularly interesting or relevant?
Yes, I pointed out, but I pointed out as a belief as opposed to possible belief. A truth will be something which is not going to change, no matter what I add to my program. Of course, whatever I add is consistent. Does it make sense?
Yeah, I think it's important to make a difference between the facts we believe are true, because no one has maybe the ultimate decision on what is true, and hypothetical reasoning. Hypothetical reasoning is a tool saying, if we were to do this, what would happen? Or if this were true, what would happen? So it's nice to have systems in which you can distinguish between what is believed to be true and what is hypothetical reasoning for the purpose of arguing.
Well, that's if you don't mind, I think that's a great discussion. One that we can build upon in other discussions later. So, may I propose that we move on to the? Thank you very much, Michael.
Thank you.
Yuanlin, are you ready on your mark? Get set, go.
Yeah. So can you hear me? Bob, can you hear me?
Yes, we hear you loud and clear. Thank you.
So first, I want to have some quick comment about the topic. So I think several of us realize it. Probably we need a few definitions. What is logical thinking? What is reasoning? What is programming? In fact, that's a master step when people try to teach something in the education research or community. For example, when they teach math, they have to define what is mathematical thinking so that they can really do the rest. So that's just a quick comment. Another comment is people realize that also, right, what grade, right, how many courses you really want to use to really achieve. But everything really depends on the definition of logical thinking. So I think we can skip this now. Oh, sorry, I'm going so far to the learning side. I think both the basic constructs of Prolog and ASP, the variations are sufficiently good to really teach logical thinking. That's my hypothesis. So yeah. Yeah, sorry, what's this question?
Purely declarative?
Yes, I introduced this purely declarative. So also I focus on very basic constructs really shared by all this. I put less emphasis on this, logic programming. I mean, more. Anyway, I don't say anything. But by the way, I teach it in a little bit special context. Like when I teach in the science classroom, really science is a major component. So so we don't really have much how to say space or time to focus too much on logic programming. We only focus on so far we focused on objects, relationships, reading, writing, designing. That's I think that's pretty fundamental to everything. So for that purpose, the declarative reading is very good enough. We also teach variables, and interestingly, when you ask a query, just search the facts to answer the values of variables. That's interesting enough. Okay, we move on to next. In fact, I do write a paper to try to show a more systematic integration of logic to any subject. In fact, here you call it problem solving. I think in the education community, they use abstraction. That's a well-accepted concept. I mean, it's taken as a core of computer science. So I play the game like I define abstraction as this. So we must have a question. In fact, this is so funny, right? I want to make it so explicit. Once you have a question, then you need a language to do the abstraction, and abstraction is not trivial. So you need a methodology. So the methodology here, identification of objects, relations, problem decomposition, iterative refinement, those are very well established areas in computer science AI thing. And I just learned that the education research, they borrowed the idea of iterative refinement so much that they have this particular design method called iterative design. I traced the literature back to AI research, but they use it so widely in their research. Okay, so next. Sorry, can you scroll down? But once we have this kind of formalism, we can really, of course, it may be a very narrow definition of what problem solving is, but it can really help to combine everything, right? The science teaching, the computer science teaching, the logic teaching, those things. Yeah, I think I can really skip this, people. It's just some thoughts. Yeah, can you scroll down? Yeah, down. Probably next page. Yeah, next question. Yes. So yeah, as you can see, I teach mainly the facts and very simple rules. So I don't really talk too much about the syntax. I always integrate that with natural language reading. In fact, not just reading. If you look at iterative refinement, people start from natural language. When they read this, when they write using relation, when they design relation. So it's from, you have a question, you have English description, then using this methodology, you can refine your English description finally into some relations, rules, and so on. Yeah, next. Just the next question, right? If we have. There's a need to teach. Yeah, my answer is no for teaching purpose. Okay. Also depends on the purpose of the course. If it's really a undergraduate course and you are serious about this, it's something that should be taught. But in the K-12, again, depending on your purpose, just for, let's say, just for teaching logical reasoning, my feeling is we don't really need it for a long time before the student can really master logical thinking. Bob, I think I'm done.
Okay, thank you. Well, one question immediately came to my mind is what you did not emphasize rules in your little presentation. And that reminded me of relational databases. When relational databases are just facts and any logic is in the queries themselves. It's only if you kind of define a query and reuse it that you start getting something like user views, which are like rules. So have you had any experience of the distinction between using rules or just using patterns of queries, for example?
In fact, for queries, we also do simple ones. In fact, I think, sorry, yeah, our query is also very simple. We do, one context is we only teach like 10 lessons or something. Sometimes we do teach a semester long, but there are so many other things going on in the real settings. We cannot really go deep to the rules for students, although we do teach the rules. there's clear evidence that students have difficulties in writing rules. But we have a lot of interactions with teachers. I think there's when teachers try to really model a domain, we find a very natural needs of classical negation, right? You just enumerated that. And we did find a natural case of default negation, with some conversation that the teachers can figure that out. And we have very, very interesting discoveries, like when we talk to a teacher. In fact, probably everybody knows that a lot of times the knowledge is not like rules, like the atomic number of element is the sum of proton number and neutron number, right? So I think there should be, but natural language is so simple, so clear. But when you write the rules, it seems to be super non-trivial, particularly if you want to write it in a natural way. And anyway, interesting discovery from the teachers. So they really start from the relations. They found that the variables are not defined, right? Then you just introduce a definition of the variables. Then this definition of variables just becomes the body of rule. That's one very good example. I identified how we can really use very natural ways to write rules. Sorry, it probably didn't answer your question, but we didn't cover rules much in the teaching.
Okay, well, I think that raises an interesting point to be looked at more closely in the future, perhaps.
Yeah, it needs a longer. It needs a lot more sessions. Definitely, we will need the rules.
Yeah.
And yes, for simple rules, I think students are okay. They can manage it. What I'm impressed is students can really talk about things in the logic required way. My feeling is they just didn't have any chance to practice this capacity. So I think the logic approach really provides the opportunity for them.
Well, thank you. In the interest of sticking to the schedule up to a point, may I suggest we move on to the next speaker? So thank you so much. Thank you. So Gopal, you are the next person on our program.
Thank you, Bob. So most of my teaching to non-university students has been to, I would say, 8th through 12th grade students. And so these students generally come to me, during the summer workshops, in the sense that they're already motivated. And an artifact of that is that they already know programming in some traditional languages and they basically want to learn more, mostly about, AI, especially in the last few years. So my sample is sort of biased in the sense that, if I picked, say, a 8th grade class in a middle school, then I will have students who are interested as well, students who are not interested. And it'll be interesting to see how students who are not interested, how they will react to, being taught logic. So in that sense, I'm getting students who are really motivated. So, I mean, my experience, you could say, is, sort of biased in that sense. So I appeal to programming, knowledge of programming quite a bit in teaching. So my responses are very much, similar to Michael Gelfond's, except that I start out with Prolog, the family database, and essentially teaching them declarative thinking, which I meant logical thinking to mean. So logical thinking, I took it as essentially writing the program declaratively, viewing them as formulas in logic. And then of course I also teach them a little bit of procedural semantics, where I show them how, given a goal, you would simply execute it by matching primitive simple unification and then replacement of goals and so on. So I actually teach both declarative and procedural semantics to these 8th through 12th grade students. And then after some time I switched to answer set programming, introduce negation as failure, strong negation, all the default rules, constraints, And there I try to teach, so there try to connect more with their, day-to-day thinking, and then try to explain that essentially human thinking processes, say you're given a goal, and of course you have these rules in your mind, and you reduce the goal by using these rules, but this goal expansion may be stopped because you encounter an exception. So, default rules, exceptions. But then what can happen is that as you reduce your goal and you accumulate these sub goals that you have to prove, then you may have situations where two sub goals may appear that are inconsistent. So then I bring in these global constraints as well. And then eventually, you may end up in a situation where you don't have information about something, and then you can make assumptions. And so I try to teach these even loop over negation in answer set programming as assumption-based reasoning. And that seems to work well. And then, of course, take problems, standard problems, and many from Michael's book, excellent book, and then try to show how these problems can be, you can write answer set programs, using this insight. And that seems to work well. And then, of course, it's an ongoing quest to collect good examples, and then, how they can be coded up in Prolog and answer set programming. But these examples are such that, students can just relate to them. Okay, so moving to number 2. So yes, so problem solving has to be taught, and I even teach them recursion actually. And so while teaching databases, teach them ancestor, and then try to appeal to, how recursion is actually a very good tool for problem solving. And you can, write, if you use recursion, then your code is more succinct, and, that sort of stuff. And then, like Michael, try to tell them to first refine their thinking, write it out precisely as possible in English, and then, convert it into code. And then, of course, formal. So already I'm teaching them declarative semantics and a little bit of procedural semantics, but of course, no formal semantics. So, so whatever is taught is very informal. But in general, yes, formal semantics, these students are not ready for that. So I basically, teach them declarative thinking, problem solving, but I do appeal to their knowledge of programming, because, those are the students I have, so that they can understand, how things are progressing, as a Prolog program is executed better. And increasingly, so I used to teach list processing as well, but now, this summer when I taught, I actually did not, teach that. I'm trying to, keep it more declarative, and basically teach more about knowledge representation and building knowledge bases, rather than, teaching them things like list processing. I think that's more or less it.
Thank you. You place quite a bit of emphasis on generating assumptions when you have incomplete information, and using ASP even loops, I suppose, to implement that. Isn't that a bit like using cut in Prolog to implement conditionals, if then else? So doesn't that disturb the declarative semantics? Because declaratively you want to reason it with assumptions, but because you don't have them as native constructs in ASP, you code them up using even loops.
Basically, I try to explain that, even loops can be thought of as, that, you're sort of programming with assumptions, and so each assumption will produce, different worlds, different stable models, you could say.
So from that point of view, in the same way that some of us are arguing that we should get rid of cut in Prolog and use higher level constructs that cut can use to implement. Maybe we should get rid of even loops in ASP and provide assumptions directly as native.
So that could be a subject of discussion, sure.
I believe you can just use disjunction instead of even loops. That's what sparked that.
That's another
possibility,
yes. Another possibility.
Okay.
I think Michael Genezareth would have something to say about that, because he's also argued in the past that one of the things that distinguishes logic programming from first-order logic is the lack of disjunction in logic programming.
So I also try to teach, deduction, abduction, and induction as well to the students, so that so the goal is again to try to have their everyday thinking fit into logic programming or vice versa. So you remember, this computational thinking, logical thinking, the whole idea is that, they can understand their day-to-day thinking and more clearly. So I've been moving more and more towards that, from, a lot of it is covered in my paper that I presented in last PEG workshop.
Thank you. So, Veronica, I think at this point we should have a decision whether to continue next week, maybe with the remainder of this discussion, and perhaps move on to a few administrative matters, or whether to try to pack everything in to today's
The only
meeting.
administrative matter that is more or less time sensitive, because the deadline is approaching, is we have to present a proposal for the conference for next year's Prolog education workshop, if we're going to have one. And that involves choosing chair people and the committee and writing a proposal. If we can do that offline, that's fine. We can continue now.
But even if we do continue now, will we be able to finish and do justice to the topic?
So if we can appoint a chair, Veronica, or co-chairs, I think that would solve 80% of the problem.
The rest is there easily. We have proposals from previous years to know what from. So yeah, how do we go about choosing chairs?
Okay, have you just agreed that we will continue the discussion today, next week on Tuesday?
Is there consensus on doing that?
My own feeling is that this has proved, a very interesting discussion, raised a number of questions I hadn't anticipated that, might be worth doing about, and, maybe inform the discussion if we continue again next week.
Sure, there's nothing urgent administratively speaking for next week. If we can deal with how do we choose the chairs and maybe choose them, that would be great. We can do that. Can we do that in the rest of the time? And then next week we have all the meeting for discussion.
Yeah, I vote for that anyway, my personally. So if
anybody objects, does anybody object?
Well, can all the presenters return next Tuesday to make their presentation next week?
Okay.
So in that case, I suggest that we, So I suggest that we break the discussion in half and continue next week and turn to administrative matters now, and thank all the presenters who presented this week, and look forward to those who will present next week.
Thank you.
So any guests who don't want to be bored with the administrative matters are welcome to hang on or leave as they prefer.
So I'm going to stop recording, right?
Thank you.
Yes. One administrative matter that's important because it's time oriented also is people who